Hey, this is Mr. Ariel. I'm here today with the second part of the notes for electron configuration. Remember, configuration is just another word for arrangement, and the precise arrangement of electrons around an atom is really important for a lot of things we're going to learn about this year. So let's get into it. Now, last time I left you with the details about how we can use light given off by heated elements to show that energy levels exist around an atom. Now we're going to fast forward through quite a bit of science history, because for the next model of the atom, the quantum model, well, that relied on a lot of very advanced physics, calculus, and some other math to get to where it is today. Now, you don't have to learn any of that physics or math for this class. We're just going to learn about the end result of the quantum model and what it means for atoms. Now, do get this part into your notes, that the quantum mechanical model makes predictions about where the electrons are arranged around an atom's nucleus. From largest to smallest, the electrons are in the electron cloud, and those are arranged into different energy levels. We learned about those last time. They're also known as shells. And so where the new stuff shows up for the quantum mechanical model is where it specifies that electrons are then divided into subshells and then even smaller divisions called orbitals. Make sure you've got that idea into your notes because I need to move on. Now on this slide, I'm going to set up a table, and you're going to need these 4 columns. Now, we already know about energy levels, so I'm going to add in numbers for the first 4 energy levels. Sometimes you see this number abbreviated as a lowercase n. That's for the number of the energy level or the shell that we're talking about. Now, the quantum mechanical model figured out the maximum number of electrons that can fit on each energy level. And so that's going to be 2 on the first level, 8 on the second level, 18 on the third, and 32 on the fourth. Now, there are actually 7 energy levels that we know about, but I've only got the table set up for the first 4. But if I wanted to know the maximum number of electrons that could fit on the 5th energy level, well, these numbers come from the quantum mechanical model, and it has a formula that says the maximum number of electrons is equal to 2 times the energy level squared. So for the 5th energy level, that would be 2 times 5, and that gets squared. And so 5 squared is 25. Times 2, that means there are 50 electrons that can go on that 5th energy level. Now, if you've got that formula into your notes, don't worry about filling it out for the 6th and the 7th energy level. There's just really not a point. I want to focus on these first 4 energy levels. Now, each of these energy levels can be divided up into subshells. And the first energy level is very small, so it only has 1 subshell. Now that's called the S subshell, and it's called S because it's kind of spherical. Let me draw it in over here. I've got an X, Y, and a Z coordinate plane, so it's trying to be a little bit 3D. And so the electrons in this S subshell kind of spin around the nucleus, but they stay in a roughly spherical pattern. So that's easy enough to draw. So I added spherical because we definitely need to know the shape of this orbital. Now moving on to the second energy level, it's a little bit bigger, so it has 2 subshells. And so that's S and P, and S is for spherical again, and then the P right here, that's thought of as being dumbbell shaped. Or some people think it looks like a figure 8. Now I'm going to try to draw in the second energy level, but first I'm going to copy what I had for the first energy level. So there's my little 1S energy level. The second energy level has an S, but it's bigger than the first one, and so it's actually going to completely surround that first energy level. There we go. And now I'm going to add these p orbitals on top of it. So the weird thing about the p orbital is that I've mentioned it's shaped kind of like a dumbbell. So the electrons are kind of flying around the nucleus and they trace out this pattern. I mean, really, they could be anywhere inside this region that I'm shading in. And so again, that's kind of the dumbbell shape, or some people say figure 8. So that's one of the p orbitals. There's actually another one that goes vertically. And then there's a third one, kind of outlined in black, and it kind of occupies this region right here. So those are called the px, py, and the pz orbitals. If my drawing isn't doing it any justice, here's a better representation that's a little bit more 3D looking. Now moving on to the third energy level, we have 3 subshells, and the first 2 are the S and the P that we've already learned about, and the third one is called D. Now I'm not even going to attempt to draw the D subshell, but here's an image that shows you how complex those electron regions are. Don't worry, you don't have to know the shapes of the D sublevel or be able to describe them. They're really too complicated for an intro chemistry course. Now finishing out the table, on the 4th energy level we have another S, P, and D, but we have an F sublevel to add in as well. The shape of the F subshell is so complicated, I really can't even find a good image of how to show it to you. But that's okay, because we don't have to know anything about its shape. Now, remember that point I made over here that we could use that 2n squared formula to figure out the number of electrons on the higher energy levels? We'll make a note right here that the number of subshells and this S, P, D, and F, that doesn't go up as you move down into the 5th, 6th, and 7th energy level. We always have 4 from this point on, and they're always going to be S, P, D, and F. Now make sure you've got everything on this board into your notes because I need to move on. All right, now on this slide, we need to get a few details about the subshells themselves. Each subshell has orbitals. Those are the smaller regions inside a subshell that hold electrons. And each of the orbitals can hold up to 2 electrons. Now the S subshell only has 1 orbital, and if each orbital can hold 2 electrons, well, the S subshell can only hold 2 electrons. Now moving on to the P orbital, remember that's the one that's kind of shaped like a dumbbell or a figure 8. The P sublevel has those 3 orbitals. Remember I called them the PX, PY, and PZ? So if each one of these orbitals can hold 2 electrons, that means the P sublevel will hold 6 electrons total. Moving on to the D and the F sublevel, remember these are too complicated to draw out, but the D sublevel, well, it has 5 orbitals, and the F orbital has 7. That means the D sublevel can hold 10 electrons total, a maximum, and while the F sublevel, that one can hold up to 14. Now make sure you've got all this in your notes because I need to move on. Now next up is the idea of electron configuration. We've been taking a lot of notes on electron configuration for a while, but this is the ultimate point of all of that work. Electron configuration is the method used to show the arrangement of every electron surrounding the nucleus. It uses something called the Aufbau process. That's a German word meaning to build up. The first part of the process is to determine the number of electrons that we're dealing with. So for hydrogen, let's say, we can just look at the periodic table and find that it has 1 electron. The next step is to fill in the lowest energy orbitals first and then move up. You may want to use this diagonal rule handout from class. It'll help you with this process at first until you memorize the order. It's got all the orbitals written out from lowest energy at the top all the way down to highest energy at the bottom. Now the 1s level is the lowest energy orbital of them all. Remember, electrons have to gain energy in order to be boosted further away from the nucleus. And so if hydrogen has 1 electron, we're going to put it in that first 1s level. So I'll write that out as 1, and then S, and then I'll put a little tiny 1 right here. That's a superscript. Make some notes that that first number stands for the energy level, the letter stands for the subshell, and then the superscript tells you the number of electrons that are in that particular sublevel. It's really a lot of information in a very small space. Now let's do another one. Here's helium, and it's got 2 electrons, and so we can start that process over again, and we're going to start up here with the 1s. So I'll start writing my electron configuration. So we'll put 1s. And the only difference for helium over hydrogen is that it's going to get a superscript 2 right here. Now my last example on this slide is oxygen. It's got 8 electrons. And so we're going to start right back up here at the top of the diagonal rule with my lowest energy level. And so that's going to be 1s. And remember that the S sublevel can hold 2 electrons. It can't hold any more than that. And so if I have 8 electrons and I just used up 2, that means I have 6 left to place. And so now going back to the diagonal rule, we're going to go from 1s, and we're going to pick up at the next energy level, that's 2s. And so I'm going to keep going there. There's my second energy level with the S subshell. And so just like before, the S can only hold 2 electrons, and so only 2 can go right here. And so now my diagonal rule says I need to go to the next energy level with a little bit more energy. And so that's the 2p sublevel. And hold on a second, I forgot to keep track. We just used up 2 electrons, so that leaves me 4 to go. And if you remember from the previous slide, the P sublevel can hold up to 6 electrons, but I only have 4 left. And so I'm going to end my electron configuration right here with 1s2, 2s2, and 2p4. Now an important thing to note at this point is if you add up all the superscripts, 2 plus 2 plus 4, you're going to get the same number of electrons that were in the atom that we started with. It's a good way to check and see if you've done things properly. Now get all this into your notes and then let's move on. Now I want to show you one more electron configuration, and this one's going to be kind of lengthy. We're going to write out the electron configuration of zinc. It's right here on the periodic table. Zinc has 30 electrons. So I'll keep that information right up here. And so we're going to start on the diagonal rule right at the top with the lowest energy. That's 1s. It holds 2 electrons. So let me keep track of that detail. So I got 28 left. Now you don't have to do this part on your periodic table, but I'm just going to shade in hydrogen right here and helium because I used up 2 electrons. And I just kind of want to keep track of things. Now using the diagonal rule, the next place we go is the 2s energy level. So that's going to be 2s. I know that holds 2 electrons, so I'll subtract off my 2. That leaves me with 26. And now I'm going to highlight 2 more elements for that 3rd and 4th electron. Again, you don't have to do that on your periodic table. All right, so back to the diagonal rule. We're down to 2s. We go to 2p next, and that level can hold up to 6 electrons, and I certainly have 6 right now at least. That actually leaves me with 20. Now I'm going to shade in these next 6 elements, but I'm going to do it in a different color. I'll tell you why in a couple of minutes. But I just used up the electrons that would have gone all the way up to neon. All right, the diagonal rule says we keep going to 3s. And I know that can hold 2 electrons maximum. Certainly have that. Now I'm down to 18 electrons. Let me shade those 2 in. It's going to be yellow again. All right, and then the diagonal rule says we go to the 3p level next. That holds up to 6 electrons, but I've certainly still got that many. 18 minus 6, that leaves me with 12. And so I'm going to highlight in those next 6 elements for those 6 electrons I just used up. Gets me all the way to argon. All right, diagonal rule says we go on to the 4s. That's going to be here. That holds 2 electrons, and I certainly have 2 right now. 12 minus 2 is 10. So let me shade those next 2 electrons in on the periodic table. We're up to calcium now. And if you see, we're about to get to zinc. Now the diagonal rule here says we go from 4s and we come back to 3d. You might wonder if that's a typo. I mean, aren't we already on the 4th energy level? Well, we are, but the fact is that the electrons go into that 3d level. They have more energy than the ones on the 4s level. And we write the electron configuration out in order from lowest to highest energy. And so it does seem a little weird that we skipped from 4s and went back to 3d. Now remember that d sublevel, that can hold up to 10 electrons. And so I'm going to write out 3d, and it can hold up to 10, and that's exactly how many I have left. And so that's it. We have the finished electron configuration for zinc. Now along the way, I was shading in those elements on the periodic table, and I want to step back to that. Notice I shaded these elements over here yellow, and helium as well. And notice that there are always 2 side by side, except for helium separated over here on the other side of the periodic table. So this region of the periodic table is called the S block, because all elements in these 2 columns have electron configurations that would end on that S sublevel. Like hydrogen, it ended with 1s1. Now over here, notice how I shaded these elements in green? Well, do you see how this area is exactly 6 elements across? This is called the P block because all elements, with the exception of helium, well, they all have configurations ending on the P sublevel. Like carbon here would be written out as 1s2, 2s2, and then 2p2. And all those superscripts add up to those 6 electrons that we have on carbon. Now this region right here, as we approach zinc, happens to be exactly 10 elements across. And if you're catching the pattern here, all elements ending in this region, well, their electron configuration ends on that D sublevel. Last up, we didn't get to this level, but these little 2 rows down here, well, it happens to be 14 elements wide, and so it's called the F block because every element down here ends its electron configuration on that F sublevel. So if you've ever wondered why the periodic table is kind of arranged into this weird looking shape, this is one of the reasons. Now make sure you've got everything into your notes because we're all done. I hope this video has been helpful to you today, and as always, thanks for watching.